Okay, uh, welcome to part one of my lectures, and where I'll give you a general overview of how the Ginzburg-Landau functional is related to codimension 2 minimal submanifolds. Before I begin, let me thank the organizer Hoju again for all the effort he put into organizing this wonderful event, and for giving me the opportunity to speak here. So thank you. And secondly, I'd like to give a couple of apologies. First of all, because I'm choosing to focus on a very particular aspect of this vast subject, necessarily I will omit many important contributions by many authors, and I'm sorry for that. And also, parallel to this relationship between the Ginzburg-Landau functional and codimension 2 minimal submanifolds, there's the link between Allen-Kahn equation and the and minimal hypersurfaces. That direction has seen many exciting developments, especially in recent years. But due to limitations in time and space, I will not be able to say too much about that. So for that, I also apologize. So now let us get started. So I suppose I should first tell you what the Ginzburg-Landau functional is. So the setting is that we have a Riemannian manifold, compact, and the functional comes with a parameter epsilon, and it takes a complex valued function u. So given these two, we define the functional as follows. So it's the integral of a gradient term plus, maybe I should make it bigger, of a gradient term plus a potential term. So the potential term vanishes exactly when u has norm 1 and is positive everywhere else. So I'm going to call this the Ginzburg, I'm going to give it a name. Okay, so capital E I will call the Ginzburg-Landau functional, even though the term could refer to other functionals in different contexts. Okay, and this lowercase e sub epsilon is the Ginzburg-Landau energy density. Critical points are where the derivative of the functional vanishes, and that happens precisely when u is a weak solution to what I'll call the Ginzburg-Landau equation, and I'll label it GL sub epsilon. Okay, by standard elliptic theory, bounded weak solutions in W12 are smooth. So below, when I say solution, I would always mean a smooth solution. Now, this Ginzburg-Landau functional is actually a simplification of the original model proposed by Ginzburg and Landau for the appearance of vortices in some superconducting materials. And it was first studied in bounded domains in R2 with S1 value Dirichlet boundary condition prescribed. So the domain should be thought of as the cross section of some three-dimensional container for the material. Mathematically, if you look at the energy density, the potential term, when epsilon is small, pushes the map to be S1 valued. On the other hand, if the boundary condition has non-zero degree, then the map cannot have S1 value everywhere. So there's a competition between the potential term and the boundary data, and you expect to see something interesting as epsilon goes to 0. And the fundamental result on the asymptotics as epsilon goes to 0 was done in the early to mid 90s by Bethuel, Coesis, and Alain. their work spans multiple papers and a book. And I'll just state one of the results they proved to give you a flavor. So this version I'm stating is an improvement due to Struve. And actually, I'm not stating it in its full generality. But let's suppose omega is a simply connected subset of R2. And suppose on the boundary you have an S1 valued map, which is your Dirichlet boundary condition. We assume that it has some non-zero degree. Okay, and suppose for all epsilon you take a minimizer of the Ginzburg-Landau functional, subject to this Dirichlet boundary condition. Okay, then as epsilon goes to 0 up to a subsequence, the following happens. You can find points, exactly k of them, where k is the degree of the boundary map. So that if you look at the Ginzburg-Landau energy density as a measure on omega, but normalize it by a factor of log epsilon, then as measures it converges to a sum of Dirac measures supported at these points. Okay, as measures. So they actually prove a lot more. They show that away from these points, U epsilon is converging to an S1 valued harmonic map. And also, the locations of these points are not random. They have to minimize another energy. And they also studied critical points, so not necessarily just minimizers. But anyway, I want to focus your attention on the aspect of this theorem that it tells you that there's nice convergence away from a bad set where energy concentrates. Now let me make a couple of remarks. So first of all, like I said, they proved a lot more. And if you are interested in the analysis of these Ginzburg-Landau type equations in two dimensions, then I refer you to the following monographs, which could be very good starting points for exploring the literature. So first of all, there's the book by the three authors, Berthuel, Précis, and Alain. It's called the Ginzburg-Landau vortices, and it's the basic and fundamental reference. And then there's the book by Picard and Rivière, and then Sondier and Serfati. So this third one in particular contains a guide to the literature, which is particularly helpful. So next, if this is the first time you see a statement like this, perhaps the part that requires the most explanation is the log epsilon factor. And so that's what I'll turn to right now. I'll give you two pieces of information to help you put it into perspective. The first one is an example. The second one is a general result. So it is known that on R2, there exists solutions to GL1 of the following form. If you write in terms of polar coordinates, then U of R EI theta is F of R times EI theta. More generally, you can replace I theta by K theta, where K is any integer, and you also, there exist solutions of this form. And what I want to focus on is the asymptotics of the radial profile, which is the F function here. As r goes to infinity, f itself approaches 1 at this rate, and then little o of 1 over r squared. And then the derivative of f decays cubically. So these are both as r goes to infinity. Okay, so with this in mind, if you now rescale u by squeezing everything towards the origin, that is, you let u sub epsilon be this in terms of polar coordinates. Okay, then it solves the Ginzburg-Landau equation with parameter epsilon, and you can compute that the Ginzburg-Landau energy for u epsilon on a disk centered at the origin is, well, the leading term is precisely pi times log epsilon, and then you have some lower order term. So it depends on r, but for fixed r, as epsilon tends to 0, it stays bounded. And furthermore, if you do this at disks not containing the origin, then the energy stays bounded. And so when you divide by log epsilon, it tends to 0 as epsilon goes to 0. So that tells you that the energy density as a measure in this case converges, after normalizing this way, converges to the delta measure centered at the origin. Okay, so this example shows you quite explicitly how the factor arises. If you go through the computation, you'll see that it really comes from this rotational part. Okay, so next, the second piece of result I'm gonna mention to help you understand the log epsilon factor is this theorem by Gazis, Merle, and Rivière. So they too study solutions on R2 to GL1, and they impose the following condition, which you can think of as saying that u tends to 1 at infinity. But that's something that has to be proved, and they prove it. So in any case, you can show that the degree of u, remember u is a complex value function, so you can think of it as mapping into R2. So the degree at a very large circle is well defined and is fixed, independent of r when r is large. Okay, so now there's a dichotomy. If k is 0, then u is constant. If k is not 0, then again, on a disk of radius r centered at the origin, the energy would grow like log of r, and then some lower order term. Okay, so this is telling you that if you want to see something interesting, then you have to allow for some logarithmic energy growth. And in particular, there are no finite energy solutions on R2 except for the constants. So I hope these two results help you understand the log epsilon factor to some extent. So let me pause here for a few seconds, and then we'll move to the higher dimensional case.